Okay, is that better? Can you hear me?
No, we could hear you, but it's more for the record.
Ah, okay. The problem is that my glasses interfere with this. Okay, it's tilted, so if I'm looking at you funny, it's because okay, great. So I just told you a little bit about my background, and so that leads into the disclaimers because there are lots and lots of experiments in this landscape, and so I'm only going to be talking to you about a few of them. I'm happy to talk about others if you want, but I'm not including them all, and so don't be offended. I also include some references, but not a lot of references in the slides. So if you want more references, ask me about that later. And I just also want to thank a bunch of folks who I stole a bunch of images from. Okay, so moving forward, my expectation is that you ask lots of questions. I already saw you doing that earlier today, but please keep doing that. And I also am very happy to have the discussion be guided a little bit by folks' interests. So if there's something that folks really want to have a deep dive on, we can do that more in the very last lecture or talk about it now. Okay. So what am I actually going to talk about today? So I'm going to give an overview today. So this is going to be about wave dark matter detection generally. And then I'm going to focus in on axion interactions with photons, because I think Sergi is going to tell you a little bit about axion interactions with other particles more later this week. And then I'm going to be telling you about a lot of experiments that are actually not dark matter experiments. I'm going to give sort of the overview about different ways we can look for axions from different sources. Okay. So you've already heard about this morning, but I want to go back over this to give the context for how we actually can detect wave dark matter. So what is the definition for wave dark matter? Well, basically, you can have the de Broglie wavelength is larger than the average particle separation, or equivalently, the occupation number is greater than 1. So last week, you heard about particle dark matter. You have lots of disconnected blobs. And this week, you're learning about wave dark matter, where you can think of it as the whole coherent field acting together. Okay. So then to make this a little bit more quantitative, what does this actually look like? So we have the de Broglie wavelength, 2 pi over mv, and you can compare that to the occupation number, which is dependent on the density of dark matter, the energy density, rho dm, again, the mass of your dark matter particle. So we're talking about very low mass particles, so m is very small. And then the de Broglie wavelength, which of course is given over there. So to turn this into actual numbers, if we're thinking about an axion, so axion, say a nano EV particle compared to a WIMP, say a 100 GeV particle, you can see that their de Broglie wavelengths are very different. And the result is that you have many, many, many orders of magnitude difference in the occupation number, right? So occupation number for WIMPs, something like 10 to the minus 36, super, super small, whereas 10 to the 44, we're talking about very, very, very high occupation numbers. And again, we're looking at this as a coherent field. Okay, so I'm going to pause here and say, what does this actually mean for how we build our dark matter detectors? Can anybody give me any thoughts on this? What's going to look different? And you heard about this a little bit this morning, so I think y'all should have some idea. Yeah? Yeah, exactly. And the reason that you can't detect sort of individual scattering events is that scattering would be tiny, totally not detectable, right? Your thresholds are way below, the threshold for any individual sensor is way below what you'd actually be able to detect for, say, a nano EV axion. Okay, good. So just to summarize, so we have a coherent wave with very high occupation number, and so we can describe this field of dark matter just in terms of classical waves. And so we look at the collective interactions of this entire field instead of these individual particle scatterings. Okay, and so I think you've already talked about this enough, but basically I like to have this sort of schematic picture of this when I give like normal talks. Basically, you can think about the WIMP picture as like a pool table where you have different balls scattering on the table and you detect something that an interaction happened if, say, like a ball goes into a pocket, whereas for waves where the particles are wave dark matter where the particles are way too light, you're looking for the coherent interactions. This is more like a windmill where you have the entire wind stream actually interacting with your windmill to see an effect. Individual air molecules, again, would not have something that you could detect. Okay, so what are the actual candidates that we can think of when we're talking about wave dark matter? You can think of lots of different things, but I'll just talk about three. So we have QCD axions, which I think is pretty much everybody's favorite candidate because they solve the strongest CP problem, which you'll hear about a little bit later. Axion-like particles, which are basically the same quantum numbers as QCD axions, and then dark photons, which are vectors. So what's the actual difference between QCD axions then and axion-like particles when you're detecting these particles? Well, really, it's just the same thing. You have to build the exact same detector to build a QCD axion and an axion-like particle. It's just that QCD axions, you know what the coupling strength is going to be based on the solution to the strong CP problem. So basically, the coupling strength is going to vary with the axion mass. Whereas for an axion-like particle, you don't have that restriction. Okay. And then I will note that some of those same axion detectors can also detect dark photons, but not all of them can. And so that's because, again, dark photons are a vector rather than a pseudoscalar, and so you don't have the exact same kind of interaction. And so I'll try to point out a little bit later which detectors actually can work for dark photons and which ones cannot. Okay, so you can write down the Lagrangian of axion interactions, and there's a bunch of things you can write down. But unfortunately, all of these interactions are very feeble. All of these different coupling constants are inversely proportional to a very large energy scale, F sub A. And again, I think you're going to hear more about this from the theorists later, so I won't dive into details about what F is, but just think of it as a very, very large number, which means that these are all very weak interactions. And so they're harder to detect, but it also means that they act like dark matter. Okay, so most experiments, including the ones I work on and all the ones that I'm going to tell you about today, look for the interaction between axions and photons. Does anybody have any idea why this might be? Yeah. Sorry? That wasn't the answer I was looking for. I'm not quite sure what you mean by that. Yeah, we can create regions with a lot of photons. I think really the thing is we have very good technology for creating photons, detecting photons. And so in fact, if you look at a lot of the experiments that are doing these other couplings, they're actually sort of indirectly using photons as well. And so QED has been around for a long time, and we've been detecting photons and electric signals for a long time. Okay, so I'm going to dive again more into this axion-photon coupling. So this is what we call the Primakov effect, where you have this axion coupling to two photons. Axions don't have electric charge. They can't directly couple to the photons, so you have some sort of loop that you have to do this coupling through. And so we just mark this as an effective GA gamma gamma. How strong this coupling actually is depends on what you can actually put inside this loop. And so that's where you have some theoretical uncertainty for the QCD axion about how strong the coupling is based on what other particles might exist. Now, this is the most generic diagram, but if you're actually writing down a diagram for, oh, sorry, yeah, go ahead. Yeah. I'm not sure I'm following. Can you ask the question in a different way? Maybe one of the theorists has a better answer for this than I do. Okay.
When we calculated it, you can multiply these terms. So you calculated it, and then the string over someone told them has to be zero. So like apparently it's number of theory.
Okay.
You gave it this calculation.
No, please. I encourage more questions. Does anybody have any other questions while we're here? I've been sort of breezing through this background material. Okay. So again, this is just the generic diagram, but if you are thinking about it in terms of an experiment, often you draw it more like this, where you have some virtual photon that's supplied by a magnetic field in your lab, maybe the Coulomb field inside a star, and then what you really think of is the axion converting to the photon in the presence of this external field. So this is what this actually looks like more schematically. So you have some classical magnetic field. This is basically a sea of virtual photons. And then you can run this either way. Either you have a photon coming in to this sea of virtual photons and you have an axion come out, or you can run it the other direction where you have an axion come in, it interacts with that sea, and then a real photon comes out. Do you have another question? Great. Yeah, you could have quarks in that loop. Yep. Okay, great. So yeah, this is what, like I said, what's called the Primakov effect. And actually, the Primakov effect, I believe, was originally named because you can have a pion do the exact same kind of interaction. Oh, yeah.
They don't have to go that much over.
Yes, yeah. They can be quarks. And so that's one of the differences between like DFSZ and KSVZ is like what quarks are inside there. Yeah. Okay. Okay, so with that diagram, you can rewrite the Lagrangian for E and M. Or rewrite the Lagrangian for QED. And basically you end up with the addition of this orange term right here, which is this FF dual coupling. And you can see right there you have GA gamma gamma, which is that very small coupling constant, and then you also have the axion field. You can then rewrite this in terms of E and B, because we're making a classical experiment. You can see something that looks like this, where you have E dot B, which again is not a term that shows up in the classical QED Lagrangian. And then you can see what comes out if you just rewrite Maxwell's equations. Okay, so here is the modified version of Maxwell's equations if you have axions interacting with photons. And so again, everything in orange is new. You have some terms that have this gradient of A, and some of them that just have A. Okay, yeah, once again, GA gamma gamma is very small. That's why we haven't seen this already. It's a very small modification to Maxwell's equations. Okay, the first thing I'm going to do when I'm looking at these equations, I'm trying to figure out what a source is for me to look for in my detector, is I'm actually just going to get rid of that grad A term. Now, not every experiment does this, but we expect grad A to be much smaller than A. And so what we'll do is we'll just actually focus on this term here, which is the remaining term. That's the strongest term we can expect to look for. Okay, so that's Ampere's law. If we take this, what we can do is we can rewrite that dA dt term as an effective current that we can look for in our detector. Because you can see basically, you can just rewrite it as if it was a displacement current or a current. Okay, so once again, we have J effective as G gamma gamma, dA dt times B, where B is some magnetic field that we're supplying for the axions to interact with. I will note, sometimes it makes more sense intuitively to just think about this as a current. Sometimes it makes more sense to think about it intuitively as a changing electric field, depending on what frequency range you're in and depending on what the actual sort of form factor is of your detector. Okay, and then you can plug in whatever the known form is for the axion field, and you can get something which is like more obvious that this is actually, or rather that you can write down what the signal should be. So we have a small signal because there's GA gamma gamma. We know that if we have a higher density of dark matter axions in our detector, we're going to have a larger signal. So that's the square root of 2 rho dm. We also know that this is a signal that is going to oscillate with a frequency that corresponds to the axion mass. Okay, but we don't know what that axion mass is, so we're looking for a signal that's oscillating at an unknown frequency. And it turns out that that's really the crux of a lot of these experiments, is we don't know what frequency signal we're looking for. And then finally, again, we have something that's proportional to the magnetic field that we supply in our experiment. Yeah. Mm-hmm. Yeah.
You're talking about quantum concentration. So exactly calculating. Now it's true that we write the Lagrangian typically, right? talk about more, whatever it means. So you can of course use a term that runs through as a Fox state. Specifically, what she's doing here is to say, computation as well. That's no. So the Fox state is, like, so it's what you're doing, right? So if you look at the experiment, the experiment cares about the actual state of the atom, because they'll be using it to build up an amplitude of electromagnetic waves in a cat or whatever. That is clearly to say plausible calculation using the total state. If it was in fact a pure particle like atom, but
Right, this current is the coherent effect of many axions ringing up this current signal. Exactly as Sajid said. Questions there? It's good we're making the connections between the different lectures. Yeah. Right. After time's longer than the coherence time, you stop adding coherently and you start adding incoherently. That's right. Yes. Yeah.
So you could take a plausible field now to say coherent state of matter, but that can still be a random thought, right? So you can have like one phase out here from this side, like take a bunch of radio stations, right? Each radio station is coherent, but like if I have a bunch of them, it becomes classically coherent, so the phase down gets random. So when she says coherent, lack of coherence, you're still in a quantum mechanically coherent state. Okay, but it's just a classically coherent.
Yeah, we'll try to point out when I mean it's incoherent because of the velocity distribution. But if you're confused, ask, and we can make sure we iron out which one we're talking about. Okay. So using this then as our signal, we can figure out what are all of the ingredients we actually need to build an experiment. So the first thing we need is we have to have some sort of EM field in order to have this interaction where we have the Feynman diagram where you have the X, right? So typically you have a very strong magnetic field when you're building a dark matter experiment, but some experiments will use an RF field instead. And then if you're talking about astrophysical searches, sometimes you're talking about like the E field between your atoms and things like that. So you need some sort of very, very strong field. And I might accidentally say magnetic field because the experiments I use magnets, but you can generically have any EM field. Okay, so once you have your very strong field, you're going to end up with a very small signal. And so you need some way to couple that very small signal into your actual detector. And again, this depends on what the frequency is of your signal and the form factor of your detector. But this is generic. You need some sort of coupling system. And then the last thing you need is a very, very sensitive sensor in order to read out that really tiny signal. So like I said, this is generic, but the actual implementation can look very widely different depending on your detector. So with that, this is the parameter space that we're going to be searching. So on the y-axis, we have G gamma gamma, that axion photon coupling constant. And then on the x-axis, we have the mass of the axion. This is a very, very large parameter space to search, many, many orders of magnitude in both directions. Again, the first thing to point out is that this is all very, very low mass. We're below the level of any of the masses of the known particles with mass. The current limit on the neutrino mass, I think, is like 0.4 electron volts or something like that. So we're very well below that. So we need very new kinds of detectors in order to detect these signals. Okay, other things to point out, we have this gold band, that's that QCD axion band. So I told you that if we have a QCD axion that solves the strong CP problem, then you're going to have a known relationship between the mass and the coupling constant with some theoretical uncertainty, again, depending on what's inside that loop. So that's that gold band. And then everything in gray are experiments or astrophysical searches, which have ruled out part of this parameter space. Although we're having a conversation at lunch about what it really means to be ruled out. Different experiments use different sort of systematics and different levels of sort of ambition, I would say, and so what they're saying is actually ruled out. And so I'm going to come back to this, and we're talking about these different kinds of searches to talk about some of the assumptions that are actually being made. Oh, yeah. Yeah, these are two different theoretical models for the QCD axion that tells you what's happening at the higher energies. And so they are two different like benchmark models, but the reason that there's some fuzz around this band is there may be some sort of theoretical uncertainties in there. Other questions on this plot? Okay. So this is what it looks like when you actually put all the different experiments here. So you can see that there's lots and lots of different blobs that are making up those gray bounds. This is from Kieran O'Hare's GitHub. I'll have a link to this GitHub later in the slides, but this is really what we all use to mark everything together. And there's a ton of data that's included on that GitHub. So I encourage folks to go check that out. Okay, so like I said, there are many different sources of axions, not all dark matter. So you can have axions produced in the lab, you can have axions produced in stars. Some of these blobs are dark matter, some of them are all these other things. And so there's a bunch of different systematics and assumptions that are going into each of these different experiments. And so when you're looking at this plot, you don't want to just take this for granted. You want to be thinking about all of those different things that are going in. Okay, so for pretty much the rest of the time, I want to be talking about all of these different sources of axions. So the first thing I want to talk to you about is astrophysical axions. So again, these are not necessarily dark matter. These are axions that can be produced in many different ways. And so those axions don't actually even need to be the dark matter. They could be something that isn't even sort of stable over the lifetime of our universe. So this is an indirect search rather than being a direct search. So we have a detector in our lab. It's not detecting the axions directly. It's detecting something that's coming from axion interactions elsewhere. Now, why would you want to do this? Well, out in the universe, not in our lab, you can have very, very strong fields. And so this is a really great way to both create and destroy axions that you're not able to actually make in your own lab. The other thing is that the entire cosmos is your laboratory, right? So if you're trying to look for a signal, you can have lots and lots of gamma rays or whatever coming from space, a lot more volume than you could have in your lab on Earth. The problem here is that astrophysics is just hard. So there's lots and lots of different systematics. We can't go out to a nearby galaxy and check to make sure we had the correct distribution of magnetic fields when we're doing our calculation. So that is a challenge. But there's many, many different targets here that you can look for and many different methods to sort of interpret the results from those targets. And so a bunch of these different sort of blobs that you see on the plot that are coming from astrophysics, I would maybe not trust any individual blob very well, but if there's lots of different kinds of blobs that are excluding different region, then you really start to trust it. Okay, so I'm going to go through a few different examples, and then I'll actually go to sort of like an activity where we can work together to understand some more of these. So the first astrophysical indirect search that I want to talk to you about is stellar cooling, because a lot of these different searches use this sort of principle, which is basically that you expect axions to be produced inside stars. So the reason for that is we have very high Coulomb fields inside stars. For example, there's lots of different reactions happening where axions can be made. But once those axions are created, they can just stream out, right? Because they don't interact very much. And so when that happens, it's a way of extracting energy from the star that's going to cool that star down. And so that's going to affect stellar evolution. So like I said, there's lots of different sort of examples of people using stellar cooling to put limits on axions. But one of the most powerful and long-standing of these kinds of searches is looking for stellar cooling in globular clusters. Okay, so what are globular clusters? These are some of the oldest objects in the universe. They're clusters of a few million stars. And because they're so old, it means that only the low mass stars remain, because basically very, very large stars burn up very quickly. And so none of them will be left over. You're just left with a nice sort of stable population of low mass stars. And so you can really identify these different stars when you're looking at them in your telescopes. So a little bit about stellar evolution, and for context, I am not an astrophysicist. So the last time I looked at this was when I was an undergrad, and it was really nice to review this. But basically, as stars live, they evolve through different stages of burning, right? So you go from hydrogen burning to helium burning, and then all the way up through these different elements. And so this is what's called an HR diagram, where on the x-axis you have the temperature of the core of the star, and on the y-axis you have the luminosity. And so basically what astrophysicists do is they can look at different stars and put it on this diagram, and then the star itself is basically going to be traveling through the diagram. But of course, we can't live for millions of years. And so when you plot a population of stars, you can see what the evolution of those stars is as they would be moving through the diagram. So the first stage that stars live through is just the core hydrogen burning phase. And so that's this main sequence right here. So you can see core hydrogen burning, 9 billion years. And then depending on the mass of the star, it's going to proceed differently. After all of the hydrogen is burned inside the core of the star, you're going to start having hydrogen burning sort of in shells moving out. That's when you get to this red giant branch. Thank you, fantastic. I'll use this is fine. Okay, yes, so you go from core hydrogen burning, it would move, if you were tracking the evolution of any given star, it would move up on this plot, and then you start having shells of hydrogen that are actually burning. And then at some point, you're going to have this flash where basically the core of the star has gotten so dense, there's so much pressure that you're going to ignite helium burning. And so then you go to this horizontal branch where the core is burning helium. And so it'll be moving through here, and then more stuff happens that doesn't actually matter for the sake of this talk. So basically, when you're looking at a globular cluster, you can do a population study where you count the number of stars in each of these places in the diagram. And because they've been around for a long time and things are sort of stable, that's going to tell you something about how long the stars will live in each phase of its life. Okay, so why is this actually relevant to axions? It's because the different stages of the star's lifetime will change how much axions are being produced. So for example, and then the one that is used most commonly when you're studying globular clusters, in the red giant branch, when you have the shells burning hydrogen, you're actually not producing very many axions. I'm going to come back to that in a second. Whereas in the horizontal branch, when you have this core that's burning helium, you're producing lots and lots of axions. And so what that means is horizontal branch stars are going to be experiencing additional cooling to axions compared to red giant branch stars. Okay, so why is that? So now we have to talk about basically axion production in plasmas. So what is a plasma? It's a region where there's lots of charges. For the purposes of this talk anyway, there's a lot more going on. But basically you have a region with a bunch of charges, and what that means is that photons cannot necessarily propagate through that easily. So what determines that is what's called this plasma frequency, which is dependent on the density of charges and the mass of your charge carrier. And basically these photons cannot propagate in this plasma if they have a frequency that is less than the plasma frequency. And so my sort of intuitive way of thinking about this, right, is you have a longer wavelength. The photons are going to be interacting with those charges as they propagate through. However, for a photon to convert into an axion, it needs to propagate for a certain distance in that field of charges in order to actually convert. So if you have a photon that cannot propagate for very long, it means it won't have the opportunity to convert into an axion. So you can only have a bunch of axions being produced if you have a situation, a plasma, where you can have this photon propagation. And so if you look at the probability for a given photon to convert into an axion, you can see right here, again, of course, it always depends on the coupling constant, as well as the field that it's inside, and then the length of distance that it's propagated for. So back to, sorry, let me all pause here. Any questions on the sort of plasmas, photon propagation, star lifetimes? Okay. Yes.
presence of electrons or other charge species, does it affect the filters?
So you can think of that density of electrons as creating this field of virtual photons. Yes. So the thing that I'm not talking about right here is the other couplings of photons. Oh, sorry, of axions. And so axions can absolutely interact with electrons and protons. So all of those things are basically systematics to these searches because you do expect there to be some production of axions from those other kind of interactions. So yes, yeah, that does matter, but not specifically for the photon coupling. It matters for those other couplings. Yeah, yeah. I'm sorry, it's a little hard to hear. Could you say? Yeah, let me see if I have a intuitive, I don't have the math here, but I'm trying to think if I have an intuitive way to talk about this. So I think you can think about it as like almost like a lifetime in some ways. So a photon has a certain likelihood over a given amount of time to convert, and it's traveling at the speed of light, and so you can immediately convert that into L. Well, yeah. Mhm. Yeah. Yeah, and that actually intuition of mixing also comes up for some of these other kinds of experiments too. So yeah, thank you. Other questions? Okay. Okay, so let's go back to globular clusters and why there's this difference between red giant branch stars and horizontal branch stars. So basically, because you have these different core densities and different core temperatures, that's changing what the plasma is inside the star. So for red giant branch stars, which have no core burning, it's only having the shell burning, the plasma frequency inside the star is going to be larger than the temperature of your star. And what that means is that there aren't a lot of photons at the correct frequency to be able to propagate inside the plasma. And so you're not going to have a lot of photon streaming, and so you're not going to have a lot of axion production. Whereas for horizontal branch stars, where you have this helium burning in the center of the galaxy, it's much, much hotter. And so what that means is that your plasma frequency is below the temperature of the inside of your star, and so you will have photon propagation. Does that make sense? Any questions there? Okay. So again, you only have axion conversion if you have this propagating photons. And so what you can do is you can take a ratio, which is the magic thing you always want to do if you're building an experiment, is if you can take a ratio. So you take a ratio of the population of horizontal branch stars to red giant branch stars. And by doing some modeling, you can use this to figure out if there are fewer horizontal branch stars than you expect compared to red giant branch stars. Okay. So that's one example of one astrophysical search. Another one that is a very powerful one is looking at supernovae. And specifically, we had this supernova go off in 1987, so supernova 1987A, which had a real wealth of information for a bunch of different fields. This happened about 50 kiloparsecs from Earth. I had to remind myself what the diameter of the galaxy was. It's about 30 kiloparsecs, so this is relatively close. And you basically expect the same thing, where you expect there to be a lot of axion conversion inside the very large fields of this supernova. So you have a lot of hot photons from the supernova. It's going to be propagating in the large B fields that are happening as you have this core collapse. And so then you'll have a bunch of axions streaming out through the magnetic fields of the galaxy, which gives them an opportunity to convert back into photons. Okay, and so when the supernova went off, there did happen to be a gamma ray telescope that was operating. This is the Solar Maximum mission. It was built to look for various solar effects, like solar, like flares and things like that. But it was operating, and so it was able to take data when the supernova went off. And by not seeing a gamma ray burst, you can place limits on the axion-photon coupling. So this is only one way that you can use the supernova to look for axions. You can also similarly, like a stellar cooling measurement, basically see if the supernova would have gone off if a bunch of the energy was being extracted by axions. But I think this is a particularly nice use of a extreme astrophysical event to place constraints on axions. Okay, and then I'm going to talk about one more of these astrophysical indirect searches, which is looking at black holes. So there's something called black hole superradiance. Has anybody heard of superradiance before? Does anybody know what that means? Okay, so I think a nice analogy for this is imagine if you have a spinning cylinder and you have a ball that hits it, it can basically extract momentum from that spinning cylinder. And you can get the same thing when you have axions interacting with spinning black holes. They can extract angular momentum from that spinning black hole. This happens sort of resonantly if the Compton wavelength of your axion matches the horizon size of your black hole. So one interesting thing about this is actually an exponential process. So if you had just like a few axions near your black hole and they're taking angular momentum from it, they're going to be sort of coming back and constantly re-extracting angular momentum from your black hole. And so you can basically form this cloud of axions around your black hole that are constantly extracting angular momentum from it. And so what's going to happen is the black hole is going to be spun down while the axions extract this angular momentum. So basically what you can do is you can go out and you can do a survey of the different black holes that you can find. And if there are black holes of a certain size that have spin, it means that there aren't axions that have the corresponding Compton wavelength. Because of this exponential process, you would expect all of those black holes to be spun down. So this is the sort of relatively model independent picture. You can also actually look for gravitational wave signatures from this, basically the axion cloud around the black hole forms this sort of gravitational atom. And so you can look for gravitational waves coming from like transitions and things like that. But that's a little bit more model dependent looking, depending on if there's like axion self interactions and things like that. Okay, so these are just a handful of very different kinds of astrophysical searches you can do. And now I want to go to a little activity portion because it's the afternoon and I think it's good to get people talking. So there's way more blobs on here than I can tell you about. So I figured it'd be nice if we could break up into small groups and do sort of a lightning lit review where you pick a blob, figure out what it's about, understand a little bit more about how they actually are making this exclusion, and then we'll come back after a little while and the different groups can report back. So I put this QR code so you can get the GitHub here. It'll tell you what the sort of source is of this data. I think maybe pairing off in groups of like 3-ish is probably about the right size. And we'll do this for a little bit. I think I'll see how they're doing before I call people back.